Welcome to the first video in our series on electromagnetic consciousness. In this series, we'll delve into a fascinating and evolving area of research that explores the role of electromagnetic (EM) fields in the brain and their potential to generate consciousness. This theory suggests a radical departure from traditional models of brain function, where neurons and their synaptic connections are seen as the primary drivers of thought and awareness. Instead, it proposes that the brain's EM fields, far from being just a byproduct of neural activity, could be actively involved in the process of producing and shaping our conscious experience. In this introductory video, I'll walk you through some of the key concepts that underlie electromagnetic theories of consciousness. We'll explore how these ideas differ from the conventional, neuron-centric views of the brain, and why some researchers believe that fields, rather than just neurons, could be the missing link in our understanding of consciousness. As we go through the presentation, you'll begin to see how this approach opens up new possibilities for explaining the binding problem, how the brain integrates different types of sensory input into a unified experience, how EM fields might influence cognition, and how this theory could help explain some of the most puzzling aspects of consciousness, such as subjective experience and self-awareness. Throughout this series, we'll dive deeper into the scientific evidence, theoretical models, and potential implications of electromagnetic consciousness. We'll explore topics such as how brain waves and EM fields interact with neurons, the role of coherence and synchronization in brain activity, and how this could lead to a more comprehensive understanding of the mind. Stay tuned as we continue to unravel this intriguing concept and challenge long-standing assumptions about how the brain works and what consciousness really is. In this slide, we introduce the idea that the brain acts as an electromagnetic generator. Every time a neuron fires, it produces not only electrical impulses that travel along its axon, but also an electromagnetic field that spreads out from the neuron. These fields are generated by the movement of charged particles, ions, inside and outside the neuron. The important point here is that these electromagnetic fields aren't restricted to the areas immediately around the neurons. They can interact with fields generated by other neurons and even synchronize across different regions of the brain. Now, let's think about why this matters. The fields generated by groups of neurons can create large-scale, coherent patterns, what we often refer to as brainwaves. These brainwaves, which include alpha, beta, gamma, and delta waves, correspond to different states of consciousness, like being awake, focused, or dreaming. In this video, we'll focus on the idea that these electromagnetic patterns are essential for coordinating brain activity across different regions, creating the unified experience we know as consciousness. Later in this series, we'll dive deeper into how different brainwaves correspond to different states of awareness. In this slide, we explore a revolutionary idea that electromagnetic fields are the medium for consciousness itself. Traditionally, neuroscientists have focused on neurons firing in isolation, but this theory suggests that the real magic happens in the electromagnetic fields these neurons generate. Instead of viewing consciousness as something that happens inside neurons, we're now thinking about it as an emergent property of the entire brain's electromagnetic field. Now, why is this important? Well, neurons are localized, they're confined to specific areas, and their communication is limited by synapses. In contrast, electromagnetic fields are non-local. They can extend across the brain, creating a medium that can integrate information from widely separated areas. This is crucial when we think about the binding problem. How does the brain take sensory information from different parts of the body, like sight, sound, and touch, and combine it into a single, unified experience? Electromagnetic fields might provide the answer by creating a continuous, brain-wide medium that allows distant brain regions to communicate and synchronize their activities. Later in this series, we'll explore how different states of consciousness, such as deep sleep, dreaming, or focused attention, might correspond to specific electromagnetic field configurations. But for now, it's important to understand that these EM fields offer a holistic framework for thinking about consciousness as something that isn't confined to individual neurons but emerges from the interaction of the brain's electromagnetic environment. In this slide, we delve deeper into why electromagnetic fields are such an attractive candidate for explaining consciousness. The first reason is their speed. Electromagnetic fields propagate at the speed of light, which means they can synchronize activity across distant parts of the brain almost instantly. This is a huge advantage over traditional neural signals, which rely on slower chemical and electrical processes. For example, when you see something, the information is processed in different parts of the brain, your visual cortex, your frontal lobe, and more. These regions need to communicate quickly to produce the seamless experience of perception. Electromagnetic fields could be the mechanism that allows for this rapid communication and integration of information. The second reason is their non-locality. Unlike neurons, which are confined to specific locations in the brain, electromagnetic fields can extend across large areas. This allows them to integrate information from widely distributed neural networks. In this video, I want you to consider how this might explain phenomena like multitasking or the experience of unified thought, where different parts of the brain seem to work together effortlessly. Later videos will show how different configurations of the brain's electromagnetic field might correspond to different types of thought or states of awareness. As we move forward in this series, we'll discuss how the electromagnetic field's ability to span different areas of the brain makes it uniquely suited to solving the binding problem, the challenge of understanding how the brain creates a unified conscious experience from diverse sensory inputs. Next, let's take a moment to look at the historical development of these ideas. In this slide, we trace the roots of electromagnetic theories of consciousness back to the late 19th and early 20th centuries. One of the pioneers was Richard Cotton, who first observed electrical activity in the brains of animals. Although Cotton didn't connect this activity to consciousness, his work laid the foundation for later discoveries. Fast forward to the 1920s, when Hans Berger invented the electroencephalogram, EEG, a tool that allowed scientists to measure brain waves. Berger found that different brain states, such as sleep, concentration, or relaxation, produced distinct electrical patterns. Although he speculated that these patterns might be linked to consciousness, he didn't yet have the tools to fully explore this idea. This slide highlights the contributions of Alfred North Whitehead and Carl Pribram to the understanding of consciousness, focusing on their ideas of holistic, field-like processes. Whitehead's process philosophy proposed that reality is composed of dynamic, interconnected events, with consciousness emerging from a holistic process rather than individual components. He emphasized the relationship between the physical and mental poles of experiences, suggesting that consciousness is a field-like phenomenon where events continuously influence each other. His ideas laid the groundwork for future theories of consciousness as an emergent, unified whole. Pribram's theory proposed that the brain processes information holographically, using wave interference patterns to encode memories and perceptions. He suggested that brain function is distributed, with waves and fields guiding cognition in a non-local, quantum-like manner. His theory bridged neuroscience and quantum concepts, influencing later models of electromagnetic consciousness. In this video, I also mention Carl Pribram, who, in the mid-20th century, developed the holonomic brain theory, which suggested that the brain processes information in wave-like patterns. Pribram's theory shares similarities with modern electromagnetic theories because it also emphasizes wave-based activity, although his focus was more on holographic processing. Later in this series, we'll revisit Pribram's ideas in more detail, especially when we discuss how EM fields might encode memories and perceptions. Both thinkers contributed to the idea that consciousness arises from complex interactions of waves, fields, and patterns, creating a unified experience beyond the sum of its parts. Now, we explore the intersection of quantum physics and consciousness. The idea that reality consists of interconnected fields is not new, and David Bohm's implicate order theory suggested that reality itself unfolds from a deeper, field-like order. Although Bohm's work was more focused on quantum mechanics, his ideas resonate with the concept that electromagnetic fields in the brain could encode conscious experience. In this video, I'll also briefly mention Penrose and Hameros's orchestroar theory, which touches on how quantum events might interact with the brain's EM fields, contributing to consciousness. While this theory is more focused on quantum phenomena in microtubules, it opens up exciting possibilities for understanding how consciousness might emerge from a combination of quantum and electromagnetic processes. Later in this series, we'll go deeper into the relationship between quantum fields and electromagnetic fields, and their potential role in consciousness. Now, we explore the intersection of quantum physics and consciousness. The idea that reality consists of interconnected fields is not new, and David Bohm's implicate order theory suggested that reality itself unfolds from a deeper, field-like order. Although Bohm's work was more focused on quantum mechanics, his ideas resonate with the concept that electromagnetic fields in the brain could encode conscious experience. In this video, I'll also briefly mention Penrose and Hameros's orchestroar theory, which touches on how quantum events might interact with the brain's EM fields, contributing to consciousness. While this theory is more focused on quantum phenomena in microtubules, it opens up exciting possibilities for understanding how consciousness might emerge from a combination of quantum and electromagnetic processes. Later in this series, we'll go deeper into the relationship between quantum fields and electromagnetic fields, and their potential role in consciousness.